Hello, everyone. This will be starting chapter 7 for our lecture for Module 4. So, as mentioned sort of in classes previously, I've been toying with this idea and telling you guys a little bit about how we can use samples to estimate our populations. And I sort of mentioned this idea of confidence intervals, which is basically looking at this kind of range that we can basically say how confident we are with our sample representing our population. And today is the day that we're actually going to be exploring that concept. So when we're working with an estimate for a population parameter, whether that's a mean or a proportion, we are going to use our sample, and the way that we basically define that population parameter is going to be based off of how confident we want to be with this estimate that we get from our sample. So moving forward, we're going to start talking about how we can estimate the population mean when our population standard deviation is known. So this I actually should say known. Okay, we're fixed. The world is restored. Okay, so that concept of sort of knowing the mean and then not knowing the mean and then also just knowing the population standard deviation, that doesn't really sound very practical to us, but it gives us a great getaway into these concepts. And we'll actually be talking about what we do when we don't know the population standard deviation in later chapters. And this will sort of start to emulate what we see in the real world. But for now, let's think about how this all plays out when we know the population standard deviation. But before we go into any of the nitty gritty calculations, this chapter is going to be very calculation based. We're going to look at the meanings of different pertinent vocabulary words for this chapter, such as confidence interval, the area of estimates, as well as the critical value. So, before we even get into those, let's talk about some pertinent definitions, one of which being point estimate. So a point estimate is a number that's used to estimate the parameter. So in this case, when we're talking about estimating our population mean, we're really going to just be using our sample mean. And this was a concept that we talked about in previous chapters, but now we're going to start seeing an actual application to it. The next definition that I want you to be familiar with is talking about a margin of error. And when we're going to be talking about a margin of error, we also talk about this idea of a maximal margin of error that will be discussed in later chapters. And this will go into how much of an estimate uncertainty that we're going to be including. But before that, the margin of error is talking about like the magnitude or the absolute difference between our point estimate and the true population parameter that we're looking at. So if we're thinking about the previous definition of point estimate, we're going to be looking at the margin of error as the difference between the sample mean and the population mean. And I really want to point out this word of absolute here, or magnitude. We see that in these like these vertical brackets here. And basically what that's talking about is we're looking at the positive value between the two. So we're not really necessarily looking at if it's negative or positive, we're just looking at what the overall difference is going to be. So sometimes your sample mean might be less than your true population parameter, and sometimes it may be greater than. But here, when we're talking about margin of error, we're talking about that positive value at all times, basically. Okay? So here, the margin of error, even though we just talked about it, it doesn't really make sense inherently, right? We just talked about how the sample mean is going to be our point estimate, or basically the value that's going to be that's going to be representative of our population mean. So why are we talking about this margin of error as if we have both of these numbers? So we sort of talk about this as like an introduction to get into how we can figure it out based off of different statistical techniques, basically. And that statistical technique is going to be the confidence interval. And that confidence interval is going to be talking about, instead of looking at what the population parameter is going to be, we're going to look at how reliable our estimate for the sample mean is going to be. So by looking at confidence intervals, we're sort of reshaping our concept of our margin of error by looking at, instead of it being like how much of an error it is away, the sample mean is away from the mean, we're going to talk about how well of an estimate it can be. So just by rephrasing that mindset, we can start to look at very effective ways and practical ways that we can use margin of error. And basically with our confidence interval, we have to outline different values for how confident we want to be. And that's something that like researchers can do on their own. Typically, we have separate guidelines for those. A lot of the times we use this number of 95%, but other common ones are 90% and 99%. But we can think about our estimation for the confidence, like how confident we want to be, as between 0 and 1. 0 being not confident at all, and 1 being 100% confident. But then you're going to be like, well, Jacob, if you could be 100% confident, wouldn't you always want to choose that? And the thing is, we have to think about this scale as sort of like a concept. Just as much as it wouldn't make sense for us to look at a 0% confidence in our answer, we never will be able to get a 100% confidence in our sample mean of it being able to represent our population. As we start to get more and more confident with our answers, with our answer of the sample mean being representative of the population, we're actually looking at a wider and wider and broader boundary. And this can be represented in this figure down here, okay? So as we start to get more and more confident, we're basically looking at the area underneath the curve for this confidence level. Very similar to how we would use the area underneath the curve for determining probabilities in the previous chapter. So here, let's say that we have, I'm going to erase the yellow here. We have a confidence interval of 90%. Okay? That means that 90% of our area is going to be within these boundaries that we have denoted as negative ZC and positive ZC. So these boundaries are known, or these specific Z-scores are known as these critical values. So here we have C being defined as confidence level, and ZC being defined as our critical value. And as we start to shift our mindset about confidence levels to sort of be representative of this area underneath the curve, we start to intuitively think about how, as we increase our confidence level, we need to include more and more area underneath the curve. So if we're working with this 90% boundary, I'm going to actually change the color here to, let's do pink, okay? Our boundaries for the 90% confidence interval is going to be as bolded here in the area section, okay? And Z sub C, this would be represented as negative Z 0.90 and positive Z 0.90. Okay? And now let's see what happens if we increase our confidence level. So now let's say that we have another confidence level, and that's going to be 95. Okay, well, that means that the area underneath the curve has to be 95. And as we can see in this original, like 0.95, right, 95%. And as we see in this graph, our critical values are symmetric about to the mean, 0 here. This is a standardized curve that we're looking at. So if we want to increase our area underneath the curve, we're going to have to make our critical values more extreme on both sides. So that's going to be represented in these values here. In these boundaries, we're getting closer and closer to these tails, and ultimately the area underneath the curve starts to increase. So, including the darker shaded blue and the lighter shaded blue, we now have an area underneath the curve of 0.95. And now we can visually see as to why we cannot have a confidence level of 1, because the area underneath the whole curve, as we remember from the standard curve, is 1. So that goes over, and on top of that, we know that the curve itself does not cross our horizontal axis here. It goes on forever and ever on both sides for those tails. So we're never going to ever be able to define a critical value boundary where we include 100% of the probability. They go on to positive infinity and negative infinity. Okay, so that's why we have to settle with these numbers of these confidence levels of 90%, 95%, and 99% even. Okay. And in this next section for our lecture, we're going to be doing an example where we include these critical values and find confidence intervals.